Okay, good morning, everyone. For someone, good evening and good afternoon also. We start the doctoral defense of Brenner, Santana, Rego. This is a defense in the group. Just a minute. Okay, this is a defense in the graduate program of electrical engineering from the University of the Federal University of Minas Gerais. First of all, I'd like to thank you, all the examination board, Professor Joseph Scott from Georgia Tech, Professor Bruno Vilhena Adorno from the University of Manchester, Professor Roberto Kawakami from ITA in São Paulo, Professor Bruno Teixeira from here at the Federal University of Minas Gerais, and also I'd like to thank to Professor David Martino Raimondo from the University of Pavia, who is also the advisor of Brenner, and I'd like also to thank to Brenner for this nice work. So now I speak in Portuguese to read the ata, ok? Então, nós vamos dar início à defesa de tese de doutorado de número 367 do programa de pós-graduação em Engenharia Elétrica. O título do trabalho realizado pelo Brenner Santana Rego é Contributions to Set-Based State Estimation and Fault Diagnosis Using Constraints Untitled and Applications. A banca examinadora é composta por mim, que sou orientador do Departamento de Engenharia Eletrônica da UFMG, pelo professor David Martino Raimondo, que também é orientador do Brenner, da Universidade de Pavia, pelos membros externos, professor Joseph Scott, do Georgia Tech, nos Estados Unidos, professor Bruno Vilhena Adorno, da University of Manchester, professor Roberto Kawakami, do ITA, em São Paulo, professor Bruno Otávio, do Departamento de Engenharia Eletrônica também aqui da UFMG. Okay, Brenner, so you have more or less 50 minutes to present your work. After that, we pass to the phase that the examination board makes some comments and questions to you. After that, we will pass to the phase of the deliberation of the examination board, and after we finish the defense. Okay, so good presentation.
Okay. Firstly, I would like to thank the members of the committee for accepting the invitation for the defense. I would like to thank also my advisors, Guilherme Raffo and David Raimondo, for the guidance and support during the doctoral course, and also during the writing of the thesis. I will present my thesis entitled Contributions to Set-Based State Estimation and Fault Diagnosis Using Constraints on Application. So this presentation is organized in 7 topics. The first one is an introduction to the thesis. Then I will present the state estimation and the methods proposed for state estimation of systems in nonlinear dynamics, the methods for state estimation of systems in nonlinear measurement and invariance, the methods for state estimation and fault diagnosis of descriptor systems, a method for joint state and parameter estimation, then I move to applications, and finally conclusions and future directions. So what state estimation method is used for? They are used when we have some of the states of the system not measured. A measurement is corrupted with noise, and also when you have to take into account the presence of process disturbances and some certain parameters. There are 2 main types of uncertainties considered in the literature. The first type of uncertainty is the stochastic uncertainties, which are commonly addressed using stochastic filters like Kalman filtering and particle filtering. And we have also uncertainties that are unknown but bounded. This means that we do not have knowledge on the stochastic properties of the uncertainties. In this case, it's addressed using set-based state estimation. A few applications of state estimation are state feedback control, robot localization, and also guaranteed fault diagnosis, which can be either passive or active. In a setting containing all the process disturbances, we compute the prediction step which consists of computing all the possible trajectories of the system and gives the predicted set. Then we base it on the measurement and bounce on the measurement noise. We compute another set, which is a called set of consistent states, and the intersection of these two sets is called the update step. With respect to fault diagnosis, one common way of addressing the problem is through the design of an input sequence, such that the reachable sets of each model, each kind of fault considered in the problem, the intersection of these reachable sets will be empty. Then the output of the system will be contained in just one of the reachable sets, and this is how the diagnosis is performed. So in the literature, there are a few kinds of sets that are used for set-based state estimation and fault diagnosis. The most common one are intervals due to the computational efficiency. However, they are conservative due to the presence of the interval dependency and the wrapping effect. Also, due to the simplicity of the ellipsoids, these are used for state estimation and fault diagnosis. However, they are conservative in the Minkowski sum and intersection and have limited complexity. Similarly to ellipsoids, we have parallelotopes, which are also simple sets. However, they are, as in the case of the ellipsoids, they are conservative in the Minkowski sum and intersection, and have limited complexity. We have also zonotopes, which are efficient in the Minkowski sum and linear image. However, they are conservative in the intersection, and they are symmetric sets. When we move to more complex sets, we have the use of convex polytopes, which can have arbitrary complexity. However, they are very expensive since the operations require conversions between different set representations. Then finally, we have constrained zonotopes, which are the extension of zonotopes. They are efficient in comparison with convex polytopes. They are efficient in the Minkowski sum, linear image, and intersection. However, the methods proposed in the literature so far are limited. Using constrained zonotopes are limited to the case of linear discrete time systems only. So, wide set-based state estimation and fault diagnosis are consolidated for the case of linear systems. The case of nonlinear systems is still an open field. And as commented, if you use simple sets like intervals, ellipsoids, parallelotopes, or zonotopes, the set operations can be very conservative. Yet, if you use convex polytopes, we will have the operations become very computationally demanding. And if you use conservative enclosures to perform set-based fault diagnosis, this will lead to poor performance on the procedure. It can result in the longer time interval required to perform diagnosis. So what is a zonotope and what is a constrained zonotope? A zonotope is an affine transformation of a unitary box, which are closed under the linear image and Minkowski sum. A constrained zonotope is an extension of zonotope in which we consider additional equality constraints in the set description. These equality constraints will allow to perform the intersection efficiently, allow the set to incorporate linear equalities, allow the set to describe asymmetric sets, and if the complexity of the set is not limited, constrained zonotopes will be able to describe exact enclosures for linear systems. So what is the main objective of this thesis? Is to investigate the development of new methods for set-based state estimation and fault diagnosis for a few classes of discrete time systems, exploring the benefits of using constraints as main set representation. In this thesis, we consider main four classes of discrete time systems. We first consider systems with nonlinear dynamics and linear measurement. Then we consider systems with nonlinear dynamics, nonlinear measurement, and invariance. Then we consider the case of linear descriptor systems. And finally, we consider systems with nonlinear dynamics, nonlinear measurement, nonlinear algebraic constraints, and also unknown model parameters. This is a flow chart showing the organization of the thesis. In dark gray, the two topics that are due to time constraints would not be presented in this defense, which are the mathematical background and the methods proposed for fault diagnosis of nonlinear systems. In the thesis, we first developed methods based on constrained zonotopes for state estimation of systems with nonlinear dynamics. Then, using these methods, we proposed an affine parameterization of reachable sets to develop a method for fault diagnosis of nonlinear systems. We extend the methods for state estimation to the case of systems with nonlinear measurement and invariance. Then we extend these methods to the case of joint state and parameter estimation of nonlinear systems. We also propose methods for state estimation and fault diagnosis of linear descriptor systems, in which we propose also a new set representation for describing unbounded sets called mixed zonotopes. And finally, we apply some of the methods, or some of the proposed methods for the case of nonlinear vehicles, water distribution networks, and analytical ion cell, lithium-ion cell. Now I move to the topic of state estimation of systems with nonlinear dynamics. In this chapter, we consider a system with nonlinear dynamics in linear measurement, and we assume that the disturbances are bounded by convex polytopic sets, and the initial state is bounded by a convex polytopic set. In this case, we consider a state estimation algorithm in which the prediction step will be nonlinear and the update step is linear. In this chapter, we propose 3 new methods to compute the nonlinear prediction step, and due to time constraints, only 2 of them will be presented, which are the main ones, the CZMV and the CZFU. So the proposal in the case of CZMV is to extend the zonotope method proposed in Alamo et al., which was based on the mean value theorem, from zonotopes as arguments to constrained zonotopes. So what is the idea? Given a nonlinear function of class 1, constrained zonotopes x and w as arguments of this function, and choosing an approximation point inside the set. We have that the range of this nonlinear function can be enclosed by a constrained zonotope, which is obtained based on the mean value theorem. And the important thing here is that the enclosure is a constrained zonotope, and the last operator here is a generalization of also contribution of this case. This is a generalization of a method proposed in Alamo et al., called zonotope inclusion to CZ inclusion. In the case of the CZFU, we have the idea is to extend the method proposed in Combastel, which is based on the leader theorem, to extend from the arguments of zonotopes to constrained zonotopes. Then, given a nonlinear function of class 2, as a constrained zonotope as argument, and choosing an approximation point inside this constrained zonotope, we have that the range of the linear function can also be bounded by this constrained zonotope here, in which the constrained zonotope is computed based on the first order Taylor expansion of the function. So we have to choose the approximation points. In the case of the mean value extension, we assume that a zonotope called a zonotope required in the CZ inclusion is obtained through constraint elimination method, which requires which consists of Gauss-Jordan elimination, rescaling, and then partial solved dualization. The proposed choice based on this assumption is a Lorentz choice, which can be solved using linear programming. Then for the first order Taylor extension, we choose the approximation point. The idea is to choose the approximation point as close as possible to the center of the constrained zonotope. However, in some cases, the center of this constrained zonotope will not be inside the set, and in this case, the idea is to choose a desired center inside the set, and then compute equivalent representation such that the center is that desired point, and then it can be chosen as approximation point. And as a side note, in the thesis we derived the complexity analysis of the state estimation method proposed in this chapter and in the next, and it is for time constraints. This analysis will not be presented in this defense. So now I'll show an example involving a state estimation of a quadrilateral UV. On the left we have the dynamic equations of the quadrilateral UV, and the measurement is provided by a GPS, a barometer, a AMU, which bounds from the initial state and disturbances given by these sets here. So in the figure above, we have a comparison of the interval of the sets provided by the mean value theorem with the mean-value extension using isotopes and constrained isotopes. We show the interval rule of the projection of the set in the x, y, and z axis. And as can be noticed by this figure, the constrained isotopes can provide smaller sets in comparison to isotopes. And in the figure below, we show the radius of the sets along all the simulation time. And as can be noticed, that despite a reasonable increase in the computational time, the constrained isotopes can provide smaller sets during all the simulation. Now I will move to the topic of systems with nonlinear measurement and invariance. In this chapter, we consider, besides the nonlinear dynamics, we consider also the presence of nonlinear measurement and the presence of invariance. This kind of systems, examples of this kind of systems are mechanical systems, holonomic and non-holonomic constraints, and also when we have a case of attitude estimation, the models consider the representation of the attitude as rotation matrix or quaternions, which must satisfy equality constraints. So the proposed method is based on 3 steps. What motivates working with discrete processes in this thesis is the fact that the reachable sets of discrete processes, even if the initial set is symmetric due to equality algebraic constraints, we have that the reachable sets of the discrete system are asymmetric in general. And this kind of set cannot be captured using isotopes. So in this chapter, we consider a linear discrete system described by these equations here, in which the matrix E can be singular, and when this matrix E is singular, we will have the presence of algebraic constraints. And in order to develop methods based on constrained isotopes, we assume the knowledge of the invisible set, which is a set containing all the states of the system during all the simulation. This is clearly a limitation of this method, which not allowed to apply the proposed methods for the case of unstable systems. And also we consider a variable, in order to develop the methods in this chapter, we consider a variable transformation based on SVD, which can use it to write the system in this new state representation. So for the prediction step, we develop in the thesis a method which provides a constrained isotope enclosure as an enclosure of the prediction step, without requiring rank assumptions on the system, which is already an advantage when experimental methods in the literature. Normally, methods in the literature require to make many rank assumptions on the matrix of the system. And also, since we are using constrained isotopes, we are able to incorporate the algebraic constraints exactly in the set description. Since the update is linear, there's nothing different here from the classic case of linear state estimation with constrained isotopes. This is solved using generalized intersection. And since the estimation is being done in a different state space to obtain the estimated set in the original state space, we require a variable transformation. So to solve the problem of active fault diagnosis of the procedures in constrained isotopes, for the different models describing the different types of faults, we compute reachable output sets based on the proposed method for the prediction step in the state estimation. So the idea here is, using theorem 7.1, it's possible to prove that an input sequence that leads to an empty intersection of the reachable sets, this will be satisfied if and only if this second condition, which is a not inclusion, is a isotope is satisfied. Since the second set is a isotope, we have a similar case of the method proposed in Scott et al., and therefore this problem can be written assuming that we choose a cost function as a quadratic function to minimize any invasive effects in the system when injecting the separate input. We can write this problem as a mixed integer quadratic problem. Then, to get rid of the assumption of the admissible set, which is a very restrictive assumption, in this chapter we propose a new set representation based on on constraint zonotopes is actually an extension of constraint zonotopes in order to be able to describe unbounded sets. This set, the description is the same of constraint zonotopes, but with an addition of generators, in this case, which are unbounded. This allows, in addition to the properties of the constraint zonotopes, besides being able to compute the system exactly, we have an efficient linear image, efficient intersection, be able to incorporate linear inequalities, be able to represent asymmetric sets. Also, if the complexity of the set is not limited, we can be able to represent exactly closed linear systems. We can also represent unbounded sets with the addition of these unbounded variables. For instance, the examples of sets that can be represented with mixed zonotopes are the entire state space, strips, a hyperplane. Since a hyperplane is a special case of a strip, and also the Squiggle case, which is an intersection of strips. When we have an intersection of strips which do not result in a bounded set, and this kind of set can also be represented using mixed zonotopes. So we developed a prediction step for linear discrete procedures using mixed zonotopes, which also do not require rank assumptions. In this case, also the algebraic constraints of the system can be incorporated, and in addition to the case of constraint zonotopes, we do not assume anymore the presence of a divisible set. Instead, we assume the entire state space in place, which will allow to perform state estimation of unstable systems. In the same direction, we can also remove the assumption of knowing a bounded initial set. We can use entire state spaces. It can be represented as a mixed zonotope. The update step in this is the same from the case of constraint zonotopes, and also between this missing closure in the origin state space is the same operation. For the case of fault diagnosis, in this case, we computed the reachable outputs of each system or chief model describing the fault of the system, and using theorem 7.2 and name 7.4, it's possible to show that this intersection will be empty if and only if a not inclusion is satisfied with the right-hand side given by mixed zonotope. But under certain conditions, we also show that this not inclusion condition is equivalent to the second not inclusion condition, which the set in the right side is a zonotope. And since the set is in the right side is a zonotope, we can also write the problem as a integer quadratic problem, similar to what is done in Scott et al. So now I present an example of state estimation of the discrete systems, in which the discrete system is described by this variable, by this matrix here, and we consider the sets as bounds on the initial state and disturbances, and this is the sets are limited to this complexity. So first, we showed an example of a bounded of the system when we apply a bounded input. As can be noticed by the figures, we compared the proposed methods with a method based on zonotopes, and the zonotopes provide a much bigger enclosure in comparison to the proposed methods. And in the first step, the mixed zonotopes provide an unbounded enclosure denoted by the arrows to infinity and minus infinity. However, with time, the sets obtained using mixed zonotopes, they converge to basically the same sets provided using constrained zonotopes. Now, now we apply unbounded input to the system. In this case, we cannot have the assumption of the admissible set, since the states of the system will not evolve inside a compact set anymore. So here, since you cannot apply the method, I only showed the results using zonotopes and mixed zonotopes. And as in the previous case, mixed zonotopes are able to provide much more accurate enclosures than zonotopes. Now I move for an example of fault diagnosis of the discrete systems, in which the nominal model is the same model considered in the state estimation example, and we consider different models for faults, one model for a structural fault, then a model for a fatal fault, and a model for sensor fault. We consider this optimal criterion, which is just a quadratic function of the input sequence, which will result in a minimum energy of the designed separated input. Here I show the results of fault diagnosis obtained using constraint zonotopes. As can be as can be noticed in the figure, first, we were able to obtain an input sequence of length 4, which separate the input. Length 5, if you consider the input times 0. And after 4 steps, can be noticed that the reachable sets are separated. And if we look at samples, samples which are propagated to the system dynamics, the samples are indeed separated. Now I move to the topic of joint state parameter estimation. In this chapter, we consider a system with nonlinear dynamics, nonlinear algebraic constraints, and nonlinear measurement. We consider the presence of algebraic variables and also the presence of unknown model parameters. We consider assume the knowledge of bounds on the algebraic variables, and also assume initial bounds for the unknown parameters. Besides examples of this kind of system, besides the previous examples involving invariance, we also have the example of battery packs, in which you have certain parameters, and we have the parallel currents, which are algebraic variables. So in this chapter, we propose a unified framework to solve the problem, in which the idea is to preserve the dependencies between states, algebraic variables, and parameters. These dependencies, they arise from the algebraic constraints of the system, and also from the measurement equation. The proposed method consists of 3 steps, as in the case of the nonlinear invariance, consisting of the prediction step, consistency step, and update step, which the idea is to use a unified enclosure for all the variables, as highlighted here in these equations, and in order to be able to propagate the dependencies from one step to the other. So the joint prediction is given by this identity here, which preserves the dependencies of the variables from the previous step to the next. The joint consistency is given by this identity here, which the idea is basically the same to preserve the dependencies. Both the prediction step and consistency step in this chapter are computed based on the mean value theorem. And the joint update is very similar to the joint consistency step, and it is given by this identity here. Since these methods are based on the mean value extension, the proposed choice for approximation point is the same. Now I'll show an example with nonlinear dynamics, nonlinear measurement, and nonlinear algebraic constraints. The considered system in this example is given by these equations here, which have the nonlinear dynamics, nonlinear algebraic constraints, and bilinear measurement. The bounds considered for the initial state, the algebraic constraint, parameters, and disturbance are given by these sets here, and we apply a sinusoidal input. So here I show a figure of the evolution of the state enclosure for some time steps. Here we compare the proposed method without defining the parameter enclosure, a method which we call the naive method, which refines the parameter set. However, from one step to the other, we ignore the dependencies between the variables and the proposed joint framework. As shown in this figure, the enclosures obtained in the joint framework they are smaller than the other sets, the sets provided by other methods. The figure to the right, it can be noted the figure showing the volume of the sets. It also can be noted that the method that they provide the more accurate sets is the proposed joint framework. So here in the figure to the left, we have the enclosures provided for the algebraic variables, and it can be noted the best results are obtained using the joint framework. And the figure to the right, can be noted that the proposed joint framework is the only one able to refine the parameter set. Now I move to the topic of applications. The first application consists of path tracking of suspended load using a two-rotor AV. For state estimation, we consider the use of constraints on topes, and differently from the theoretical case, in this case we have sensors with different sampling times. We do not measure the load position and velocities, and the load position, orientation, and velocities. And due to the complexity of the nonlinear equations describe the system, we opt to use the linearized dynamics to do state estimation. To perform the state feedback control, we propose a minimum variance feedback in order to choose a point inside the estimated set based on Kalman filtering equations. The closed loop system must be robust to external disturbance, and we propose the use of a discrete time mixer 82 and 16 control to solve the problem. Now I show the video, a video on the results. Okay, first, the experiment starts with the takeoff in a spiral. The idea is the load for the load to follow a specified trajectory under the effects of external disturbances. Now, the trajectory is a straight path, then we have a sudden direction changing in direction. Now, a second straight path, then we will have a second change in direction, then a third section of a straight path, and then finally we will have a procedure similar to landing. The second application considered in the thesis is the case of water distribution networks. Water distribution networks in the thesis are modeled as a set of nonlinear algebraic equations. If the objective is to obtain accurate bounds on the water flows and pressures, given known bounds on the uncertainties, which is the case, in this case are the reservoir tank levels, the water demands, and also the pipe parameters. The second objective is to use these obtained bounds to detect leakage. So in this chapter, we compared four methods. The first method is a previous method proposed in Brackins et al., which is the interval method. We propose the application of a considered top step to define an enclosure to obtain more accurate steps, and we call this IHISECZ. We propose a different method, different interval method based on the scale, which will be more efficient. However, we provide a little bit more conservative enclosures than the previous method. And we propose also to apply constraints on those as a final step. The work presented in this chapter is a collaboration with student Stelios Brackins and Professor Myers Policarpo from the University of Sussex. Here I show one of the results presented in the thesis, which consists of a transport network with 13 pipes, 9 nodes. The uncertainties are given by 5% and use EPANET to simulate the system. As shown illustrated in the figure to the right, we have that the sets obtained using constraints isotopes are significantly smaller than the ones obtained using intervals. And in comparison of the two interval methods, we have that the new method is a bit more conservative than the previous method. However, as shown in this table, the execution times of the new method are significantly smaller, which allows to apply this method in a more realistic systems with hundreds or thousands of pipes and nodes with reduced execution time. Using the closures obtained using constraints on tools, we were able to perform 20% more leakage detections. Now for the third application is the problem of state estimation of a lithium-ion cell. In the thesis, we modeled the cell using an electric circuit model with states, the state of charge and the capacitor in the voltage, in the capacitor voltage. The objective is to obtain accurate bounds on the states, which is the state of charge and the voltage, with parameters identified from a more realistic model, which is a simple particle model with electrolyte dynamics. And this work was done in collaboration with the student Rego from the University of Pavia. And the method used for state estimation is the forward backward constraint propagation method proposed in Jolan et al. Here we have a figure showing comparing the results obtained in open loop and closed loop. And by these figures, it is clear that the method in closed loop provides much more accurate enclosures for the states of the lithium-ion cell. Now I move further to the topic of conclusions and future directions. In this thesis, we were able to propose a method for state estimation using constraints on topes consisting of a nonlinear prediction step, in which we proposed three methods, the CZIB, CZMV, and CZFO, and these three methods were able to provide more accurate bounds in comparison to zone topes. Based on these methods, we also proposed a method for fault diagnosis of a system with nonlinear dynamics, in which we were based on an affine parameterization of the reachable sets and resulted in an IQQ to be solved. For systems with nonlinear invariance, we proposed a method for state estimation using constraints on topes, which proposed methods to solve a nonlinear update step and also proposed a consistent step. The methods were based also on invariant extension first order table extension denoted by CZMV and CZFO, and both were able to provide more accurate bound comparison to zone topes. In the case of the descriptor systems, we proposed methods for state estimation and fault diagnosis using constraints on topes, which required the assumption of the knowledge of a divisible set. However, both the prediction step and the reachable sets used in these methods incorporated equality constraints, which is an advancement with respect to the methods in the literature. Then we proposed methods based on the new set representation to mixes on tope. Besides incorporating the equality constraints, they no longer required the assumption of the admissible set or an assumption of a bounded initial set. However, despite these advantages, this resulted in the longer input sequence in the fault diagnosis, which is yet to be investigated. And finally, for system nonlinear measurement, algebraic constraints on non-parameters, we proposed a method for joint state and parameter estimation, which preserved the dependence of the states, algebraic variables, and model parameters. Now I present some future directions proposed in the thesis. We propose the efficient implementation of the linear state estimation methods bioparallelization, because despite being more accurate, these methods have increased the computational burden. And the idea is to perform, for instance, implementation in GPUs. And also, we propose to perform active fault diagnosis of these systems in linear dynamics with reduced conservatism. This means to propose parameterizations different, other than the proposed affine parameterization, in order to be able to describe the reversible sets more accurately. But the main challenge is that this can result in a non-convex optimization problem. And also, we propose to perform a key fault diagnosis of systems in nonlinear measurement, nonlinear invariance, basically to use the methods developed in Chapter 5 to parameterize the reachable sets in order to design, to propose the design of an optimal separate input. We propose also to perform closed-loop active fault diagnosis of the nonlinear systems and linear descriptor systems using framework based on the moving horizon approach proposed in Raymond et al., which use measurements to obtain a better performance of the fault diagnosis. Also, we propose to perform state estimation and fault diagnosis of nonlinear systems using mixed isotopes, in which the main challenge is to compute the enclosure of the remainder 10, since the previous enclosure is an unbounded set. Also, we propose to investigate in which conditions mixed isotopes are able to provide bounded enclosures for the linear descriptor systems, and we suspect that these conditions are associated to observability properties of the system. We propose also to investigate why the fault diagnosis using mixed isotopes required a longer input sequence with respect to constraints isotopes. We also propose to perform state estimation of battery packs using constraints isotopes. Basically, since this system will be a nonlinear descriptor system, that is to use the method developed in Chapter 8, which is the joint state and parameter method. We propose also to formulate the minimum variance feedback to take into account the state enclosure in the stochastic properties. This in the application, the method proposed in the application of linear vehicles. So during this doctoral course, four journal papers were published, and another four journal papers were either submitted or yet to be submitted. And during this doctoral course, we published 6 conference papers. I would like to thank the CAPES, PPGE, CNPq, FAPEMIC, the Macro Group, and then SAC for their support in this doctoral thesis. this doctoral course. And thank you for your attention. That's it.
Okay, thank you very much for the presentation, Brenner. You did it, the presentation around 45 minutes. It's so good. So now we pass to the phase of that the examination board make questions to Brenner. And as usual, you start with the member who is farthest away from here, from the graduate program. So I'd like to invite Professor Joseph Scott from the Georgia Tech to start this phase, and also to say thank you, Joseph, for accepting this invitation. And so, your turn. Thank you.
Okay, so this is we don't go in order here, so this is caught me by surprise.
Okay.
Am I no longer allowed to ask any more questions after it's my turn?
Yeah, no. So you do the this way, no? Each member make the questions, I pass to the other one, and so on. And so we don't have a limit of time, so you can take all the time you want to make all the questions you have to Brenner. So feel free to make every questions. Thank you.
Okay. Yeah. Well, so over the weekend, Brenner, I had a chance to read through all the thesis pretty carefully. So I don't have a lot of questions for clarification. I mean, first of all, it's a really impressive amount of work that you've managed to do. It's quite a lot in the thesis that's new. So good work on that. There were a few things I didn't know you had worked on that I had some questions about. So one thing that was very interesting to me was the chapter on active fault detection for nonlinear systems. Whereas the key issue there, as you know, is that in a linear case, you get reachable sets that are affine with respect to the input. And once you compute those in advance, then the optimization problem is greatly simplified by that fact. There's a reachable set, as you change the input, then just translates around. It doesn't dilate or rotate or change shape in any way. And with nonlinear systems, that's not the case. And you did in the end come up with an affine parameterization of the nonlinear reachable set, although at a pretty bad cost, I would say. The thing you had to do there was to essentially do some parts of the reachability set bounding computation with the entire input space rather than just a single input. And so I'm wondering a couple questions related to that. You did show one application where that worked out. Do you have any further data than that on how conservative that is? And did you try other examples? And then do you have any ideas that we could pursue in the future for how to come up with a nice parameterization of that set that's not so conservative?
Okay, there was an application in the thesis of a quadrilateral regime. But yes, this reachable sets, in order to formulate as an affine parameterization, I had to compute the remainder for the entire input set, and it's very, very conservative. So at that moment, I think when I was working on this chapter, I have taught in the quadratic parameterization. That is, instead of evaluating the reachable set for the entire inputs, just one part of one part of the remaining is situated results in the quadratic function of the I believe, of the generated variables. I don't remember exactly what I did at that time. But this resulted in a non-convex problem. Like we have an equality, you have an inequality with a quadratic function of the generators and a quadratic function of the decision variables for the optimization problem. And then when I saw that, I stopped. It was this work is I think it's performed in the middle of the doctoral course, but yes, there is this huge drawback of the conservativeness. Still, I thought about the quadratic parameterization, but no, I did not reach like the end of the idea.
Yeah. Okay. Okay. So another question I have, or something that's bothered me about the work that we did together, is that in the constrained zonotope state estimation methods, we still have linear program solves embedded in some of those steps. I think this has to do primarily with generating the reference point for some of the linearization. There's linear programs being solved. And I suspect that at least with the mean value method, maybe not with the Taylor method, those linear programs are taking the majority of the computation time per step, and they're largely responsible for the negative comparison we have there relative to the standard zonotope methods. Do you have any thoughts on how we potentially get rid of those linear programs?
Yes, I agree totally. This seems, even if you look at the computational complexity that we derived, it seems that most of the complexity, maybe the biggest complexity, the highest complexity, comes from the interval rule, right? Which requires the computation of several linear programs.
Yeah.
I had an idea to solve this. Only the interval rule, not the rest, like the choices. The choices, I didn't have an idea to propose something that is not based on a linear program. It was based more or less in the rescaling, but
yeah,
I was able to obtain. I was able to test this idea, and was able to obtain, let me say, good approximation. However, in this, I tested in the methods of chapter 5, and the results were more conservative, and it was not only mildly more conservative. The results were visible, the difference.
Okay, so remind me what chapter 5 was?
The methods with the invariance.
Okay, so you tested out this idea, for example, on the quadrotor example?
Yeah, but it's not in the thesis. This test was not in the thesis, but I tested.
And the result, you say, was visibly worse, but was it still much better than the other methods?
Yes, it was. I can remember the relatives was still much better than the zonotopes, but it was visible worse than using the exact.
Yeah, of course.
And I had a very good gain in the sense of execution time. It really boosted a lot when I did that.
Okay, well, those were the main questions I had for you. I'm happy to pass it on now to the next committee member.
Okay, thank you, Joseph. So if you have more questions after, sure, you can make other questions, of course. And also, if there is some discussions between the members, we can provide that. I think it's good for the defense. Okay, so thank you very much for the comments and questions. So now I pass to the next one that is first from the graduate program. So this is Professor Roberto Kawakami. So Professor Roberto, thank you again to be part of the work of Brenner. You were in the qualifying exam and now in the final exam. So thank you very much for accepting this invitation. So your turn, please.
Well, thank you, Professor Guilherme. It's my great pleasure to be here to be part of this examination board. And I was already a part of the examination board in the qualifying examination, as Prof. Guilherme said. And I was very impressed with the amount and quality of the work that has been done since the qualifying examination. It's really an excellent piece of work that you have here, Brenner, and I do not have any doubts concerning the qualification of this work as a PhD thesis. So I just have a few comments that may be useful for you in order to prepare the final version of your thesis. So would it be possible to present your dissertation in our screen?
Yes.
Just to make some comments regarding specific pages. I did not organize, have not organized my comments in order of relevance. Rather, they are just organized in the order that they appear in your dissertation. So, firstly, this is an issue that we had already discussed during the qualifying examination. Do you think that it would be possible to account for the time discretization error in a systematic manner? Because you work with discrete time nonlinear systems, but in some examples you were forced to perform an Euler discretization in order to use the continuous time nonlinear model. Mm-hmm. So would it be possible to determine suitable bounds for the model disturbance W of k in order to account for these discretization errors?
There are some methods, not so maybe the most methods in the literature. In the case of the reachable sets, distributed analysis, that proposed for the continuous time systems, and they propose methods for mainly in the Matthias Althoff. Also, I think was the main topic, maybe one of the main topics, maybe of doctoral thesis of Professor Joseph Scott. There is this, maybe I'm not exact in this affiliation, but I'm almost sure in which there is, since the systems are in the continuous time, in this case, there are methods for computing the reachable set after a given time, say Ts, the sample time, and this reachable set will be not have this approximation given by the discretization. This is the exact reachable set. I think considering the solutions instead of the ODEs, instead of discretizing them. So yeah, using the methods proposed in this thesis, I don't think that's very direct. We need to maybe start from the continuous time and using the ideas proposed here to move to continuous time to consider that discretization somehow.
Mm-hmm. And a similar question could be posed regarding linearization errors in the aerial load transportation example. If you have a look at page 150, so at the end of the page, or close to the end of the page. You see, yeah, thank you. You say that these matrices were adjusted empirically to accommodate linearization errors. So when I read this statement, it occurred to me that you were concerned about these linearization errors and somehow tried to account for their magnitude in your method. But how exactly did you adjust these matrices to account for those linearization errors?
Okay, in this case, it was totally empirical. It's a simulation. I mean, it was not made not a formal computation of the linearization errors that will have the guarantee. It was based on the simulations themselves, verifying if the state was inside the set. This is not the, let's say, mathematically correct way to do this because we don't have the guarantee. But to have this guarantee of having these bounds contain all the linearization errors, the way to do this is to apply, for instance, the first order Taylor extension method, which is based on a linearization. However, in that method, we compute a guaranteed bound for the remainder, which is the linearization errors are the remainder of the Taylor extension, right? So the Taylor extension method proposed in chapter 4 or maybe the one in chapter 5, it will be guaranteed. It was not applied to the system because we could not have, in this case, we are linearizing for different, say, the purpose of linearizing, because at least at this time, we're not able to compute, to get the analytical expressions for the Jacobians and the hasteness of the system into the complexity of the nonlinear system. It will be required to be able to compute these analytical expressions, then use the first order Taylor extension method that we proposed in the chapter 4 or the chapter 5, and then with that we will have this guarantee in the linearization errors.
Okay. I assume that you could as well adjust the magnitude of those matrices to accommodate the discretization error as well in an empirical manner.
Yeah, it will be possible to still don't have a guarantee because it's empirical.
Now, moving on to the active fault diagnosis method that you proposed, it seems to me that in order to use that method, one would need to know the latest time k at which the system was guaranteed to be operating under normal conditions. Because to start the diagnosis process, the fault diagnosis process, you need to know that the state X is lying on a certain set xk, okay? Right?
Mm-hmm.
So, if we assume that we knew such a set at the initial operating time, say, let's say x equal to 0, you can, of course, use your set estimation procedure to propagate that initial set x0 until time k, the initial time in which you start your diagnosis procedure. However, in order to carry out such a propagation, you need to know the mode in which your system is operating. So from the initial time until the time, the starting time for your fault diagnosis procedure, you need to propagate the set, the state set, by using some known mode. Okay?
Yes.
So maybe that is an assumption that you have to add to your in the beginning of your problem statement, because otherwise such an assumption will be hidden and the reader will not be aware of it.
Yeah, I agree.
Okay.
Yes, I agree. And this problem that you are mentioning, if you, I mean, we are assuming, right? You're pretty right that we are making this assumption implicitly. And yes, if you do not assume this, the problem will be much bigger to solve. Much bigger. I mean, you extend not only to the fault diagnosis process, we will need to propose the fault, the part of fault detection, which will be done with the part with
Sure.
the passive method. However, you still have this problem of knowing the model to estimate.
Okay.
Yes, I must add this.
And regarding the optimization of the separating input, I was wondering if you consider the mechanical manipulator example, your two-link manipulator example, if the initial set x0, if the initial state set x0 were symmetrical around the origin, it seems to me, it's not the case in your example, it's not symmetrical around the origin, but let us assume that it were symmetrical around the origin. Then it seems to me that if U is an optimal separating input in that case, minus U with the sign reversed would also be optimal, because the problem would be completely symmetrical. Does it mean that you may have some settings for which the solution of your optimization problem is not unique?
Yeah, I didn't talk about this problem. Yes, you are right. Because it is not matter to be able to detect the fault moving the system either to the left or to the right. It's like this, because it's exactly the same. Yes. I conclude. I didn't talk about this in detail, but yes, the conclusion is that there will be more than one solution in some cases, or maybe in the general case there will be many solutions. Aside with the same, say, resulting in the same value for the cost function, and it's still separating the sets. It's clear.
Okay.
For me now.
Maybe that would be worth some the inclusion of some remark, because of course, if you had just a quadratic program with a positive definite Hessian, the problem would be strictly convex, and then you'd have a single optimal solution. But you have the integer variables, so I think the non-uniqueness problem is somehow related to the integer variables. So maybe you may just consider adding some remark at this point. And now moving on to page 126, this is just something that was not entirely clear to me, either in the dissertation and in your oral presentation. Page 126. Okay. Now, you are now considering the existence of algebraic variables. And I was wondering, what is the law that describes the time evolution of those algebraic variables? Are they in some sort of external time varying disturbance, or
Okay, there is no, these algebraic variables, they don't have a dynamic, they don't have a dynamic relation from one time to the other. They are static. In this sense, I mean, not constant, no. Maybe I'm using the wrong term here. We don't have this dynamic law. I mean, they are determined only by the constraints, the algebraic constraints, I mean, time instant.
And what is the difference between the nature of these algebraic variables and the disturbances of the system? Can you give me an example? That was not entirely clear to me in your example.
Yes. For instance, there is an example which is clear, which is the example of the triplex, in which you have for instance, you have several cells in parallel, and the currents of each cell will be an algebraic variable. They don't have a dynamic law. They are determined only based on they are just a result of the Kirchhoff law of currents in the point, which they. So I don't have a figure to show this, but from the input current, for instance, to divide for the several cells, there is a Kirchhoff law of currents in there, and these currents are determined only by that equality constraint. And maybe I'm missing some information maybe with respect to this, but the currents are algebraic constraints in that case. Need to have for its disturbances can be the measurement noise, measurement the voltage. You have the measurement noise and the disturbances. The disturbances are not the disturbances are external. This is the measurement noise. I mean, I'm not sure if I'm saying this for the process disturbance, but the disturbances are not determined by the equality constraints. You know, so my explanation was complete.
Well, okay, maybe you could just clarify this difference between the algebraic variables and the disturbances in the example itself. Maybe just writing a bit more on this difference between the algebraic variables and the external disturbances would be enough to clarify this issue for the reader. I was also wondering whether you considered a different approach to identify the model parameters P, the constant model parameters, because it seems to me that you could have augmented the state vector with these parameter P and assumed that this P variable follows a dynamic of the form pk plus 1 equals pk to impose that it is a constant, and then use the method that you had already devised for state estimation. Have you considered this alternate approach?
Yes, essentially they are equivalent. I mean, what is done here in this chapter with respect to the parameters, I'm not able to find here easily, but it is basically exactly what you said. At the end we are augmenting the state vector with the parameters and considering the constant dynamics, the identity matrix in the prediction. It's basically the same thing. So,
okay,
yeah,
right. So,
can be
so
seen
they're basically
as
equivalent.
they're equivalent. They are equivalent.
Mm-hmm. Now, moving on to page 146. Again, this is something that we had discussed during the qualifying examination. but it is still not entirely clear to me. You were you are considering a control example, so you actually need a point estimate of the state rather than just a set estimate, because you need that point estimate for your control law. And then you somehow use a hybrid state estimation approach. You combine your set state, your set estimation method with a stochastic estimation method, which is the Kalman filter approach. However, at the very beginning of your thesis and also at the very beginning of your presentation, you made it clear that the state estimation problem could be tackled, could be handled either from a stochastic point of view or from a, let's say, robust point of view. And it's not clear to me whether you have anything to gain by mixing, by combining those two approaches. You see, because if your goal was simply to obtain a state estimate to use in your control law, you could have used standard stochastic estimation methods, such as the extended Kalman filter or a sigma point filter, and so on. Of course, you claim that by using this hybrid approach, you somehow avoid the divergence problem, the state estimation procedure. However, there is plenty of work done on nonlinear state estimation methods that also handle the divergence problem. So, does it make sense to combine the stochastic and the set theoretic methods in this hybrid approach?
But right, the idea is to use this stochastic approach. Approach was only to choose the point inside the set. However, we could be using maybe different approaches instead of stochastic. It is, I mean, the main point here is not using the stochastic approach, but only to choose the point inside the set. We are worried to getting a sequence of points in time that will have some kind of smoothness to use for state feedback. This was the first idea, to use the equation for the Kalman filter. But the idea is just to choose a point. As a future worker, we can try different methods that make maybe more connection with the part of the state estimation, instead of just, I can say, seems this impression that the idea is to use the hybrid. But when the idea is just to choose a point that it was smooth, somehow smooth with the time. Of course, I agree that, for instance, we may try to use, I don't know, the uncentered Kalman filter here to make a point. But yeah, maybe this impression of the hybrid was created, but the main idea is just to choose a point. Of course, you can maybe, I tried only to choose like the center of interval rule here, and it was missing some kind of smoothness to do the feedback connection, because the system was unstable. But yeah, the idea here is not that we are using a stochastic approach, just to choose a point, at least the initial idea, that always has some kind of smoothness.
Okay. have you considered using, let's say, the Chebyshev center of the zonotope, which would be the center of the largest radius ball that is contained in the zonotope? I think that such a center could be obtained through the solution of a linear program.
We have to think about this. Maybe it's a good direction to go the result here.
Because it just occurred to me that by doing so, you'd be consistent with the use of set theoretic methods, and you wouldn't need to use a hybrid approach that would need some further justification or some further analysis regarding its properties. Well, it's just a suggestion for some future work, maybe. And finally, in some of your examples, when it came to the when you had to choose a feedback control law to carry out the simulations, you opted to use a state feedback control law, even though you did not have access to the state itself. So you used a state feedback control law just to generate the data to test your set based methods. So maybe it would be more in line with your assumptions to use an output feedback control law, because there are output feedback synthesis methods that you could have used to generate some sort of controller that would not require access to the state. Have you thought about that?
At that time, when I was talking about the results, the result of the quadrilateral review, right?
Yeah.
And at that time, I didn't thought about using an output feedback control law, and it makes totally sense to use output instead of the state. Yes, you are right. The idea is just to get the data and estimate, see what to apply the state estimation method, but not to do the feedback control. But can I say, doing a posteriori estimation, something like this, not a posteriori in sense of. I remember that this name means something in the stochastic framework, but it's not what I mean. I mean, I have the data, the measurements, and I will estimate the states. And yes, it will make totally sense to use an output, because we are making an assumption that we know the states, and at the same time we want to estimate the states.
Mm-hmm.
And at the end, in the practical sense, it does not. In the practical point of view, does not make sense. Yes.
Mm-hmm. Well, those were basically my comments. They were just some minor remarks that you may consider when you write the final version of your thesis. And once again, I would like to congratulate you on this work that has been done in an excellent fashion. I would also like to congratulate your supervisors, Prof. Guilherme Rafa and Prof. David Raimondo. And it was my greatest pleasure to be here. So thank you once again. Prof. Guilherme?
Okay, thank you very much, Professor Roberto. Very nice comments and suggestions. I make some notes here, and also the presentation will be recorded in YouTube, so we can perform all the comments and suggestions in the final version. Thank you very much. So now I pass to the next member of this examination board, and I'd like to invite Professor Bruno Vilhena Adorno, that's now in the University of Manchester. Until last year, he was with us here. Thank you, Bruno, for accepting this invitation. And so, Brenner is yours.
Okay, well, first, thank you for the invitation. I'm very glad to be here. I was in the qualification examination board, and at the time, I could already see that Brenner was doing a very good work. And actually, Brenner was my student in several classes, and he always excelled in all of them. So I couldn't expect a better work. I was already expecting a work like this with a very high quality. So yes, I agree with Professor Roberto Kawakami. It's an impressive piece of work, and congratulations for that. I have, minor questions. I did some comments directly on the PDF, but because they are so minor, I decided to defer them to later. So I'm not going to touch upon them. Later on, I'm going to pass the PDF to you, and then you can just read what I wrote there. Here, I want to discuss more interesting aspects of your work, especially regarding the implications and future works, actually. So one question I have for you is regarding inequality constraints. So have you thought or have you considered to extend your method to system containing inequality constraints? Is it possible to do so? Does it make sense to do so?
I think when I was working on the methods with the nonlinear invariants, besides the equality constraints, there was the first idea considering inequality constraints. And yes, it is possible, in the sense that, if I remember correctly, because I think I developed something by hand in bits of paper. Yes, it's possible to consider inequality constraints. It's a bit like they have a. Let me see if I do some similar equation here to show, to help me. Here, for instance, less or equal to 0, right? Mm-hmm. You can, if I remember correctly, you can approximate the left side by either using the mean-value theorem or the first-order Taylor expansion, similarly to what is done to the case. Maybe I did not reach the end of the development of this, but I think it's able to write like something hk less or equal the hx less or equal than k, which is the description of a convex polytopian of space representation. I am almost sure it's possible to reach something like that. Now, in practical systems with this constraint, I am not, at least at the moment, I cannot think about an example, but at least in the theoretical aspect, for me, it seems to be possible, very possible to consider.
Okay, so my question was motivated by the fact that in some fields like mine, when working with humanoids, for example, it's very common to have unilateral constraints, which are represented by inequalities. So, for example, if a robot is, trying to reach an object, and then it just touches the wall in order to maximize the support area, and then maximize the overall balance, right? So we use this kind of unilateral constraints. So they are always described by inequality constraints, which is somewhat straightforward because, for instance, imagine that you are, taking into consideration the robot's hand. It cannot go beyond the wall, which means that it's a pure inequality constraint. So those kind of constraints appear a lot, and we've been working with what we call vector field inequalities, which are just differential inequalities. And they are very useful to, impose nonlinear constraints in quadratic programs because it's a kind of quote-unquote linearization, but then you guarantee several properties. And when I was reading your PhD thesis, I was wondering if it would be possible to extend your techniques to those kind of inequality constraints, because I can see some applications. I asked if it made sense to you, just because there is the practical side, but there is also the theoretical side. Sometimes, as you mentioned, you can find equivalent systems in which, in another space, an inequality constraint can become, an equality constraint inside a set. I don't know. That's why that was my main motivation for this question.
Okay.
So, from a mathematical point of view, your final answer would be that it's feasible, right?
Yeah, it seems possible. It seems possible to do that, and it's not very different. I mean, different, but not very different from what is known with invariance.
Okay. And my second question is more related to non-Euclidean spaces, because, of course, you are dealing with Euclidean spaces, and there is also a clue here. So in this assumption in which you impose a constraint, equality constraint, to define an invariant, of course, for example, you already mentioned in your presentation that for quaternions, you just impose an equality constraint, right, which is an invariant, right?
Yeah.
But can you do that in general for whatever non-Euclidean space? Can you apply those techniques for example, for Riemannian manifolds?
I believe that as long as, of course, this consider this non-Euclidean space, I'm assuming that it can be described in the Euclidean space. I mean, in a manifold that is embedded in an Euclidean space, and the manifold is described by the invariant, right? If I don't, I think it is out of my current knowledge. But if you have don't know if it is possible to have manifolds that cannot be described in this way, then the method cannot be applied. I don't know. At least the case of quaternions, it could be described because it's an unitary norm. We can describe, let me say, I don't remember the exact terms, and you will correct me if I say the wrong names here. I know if isomorphism, right? I think the isomorphism. I don't remember anymore. It was in your classes, but I don't remember. I'm sorry.
Related to the SO3?
From I can say, from the space of the quaternions to the, let me say, R4. And maybe I didn't say nonsense.
Okay, no. Yes, actually, you have an isomorphism, but a group isomorphism, but under the addition operation. And what you need there is the multiplication operation. So there is no isomorphism related to the multiplication operation. Yes. But there is another challenge, actually, because it's usually hard to represent those kind of manifolds. And when you have multiplicative groups, like the group of rotation matrices, quaternions, dual quaternions, homogeneous transformation matrices, and other groups like that, it's usually hard to represent them in discrete spaces. Because of the topological structure of the space. So I think that in addition to the challenge of representing isotopes for these spaces, of course, if you have a very well-defined invariant, that's easy because you already done it. But I'm not sure if it's always the case that it's easy to describe those invariants. And also, I think that another challenge would be to do that in discrete time, because in continuous time is much easier when dealing with these differential spaces, right?
Yeah. The example of quaternion, I relied on the fact that you have a discretization method very specific for the dynamics that preserve the unitary norm. but it's not general. I think this is what you're saying, right? We don't have a general solution for this.
Yeah.
Like to move to the, I think the rotation matrix is very different from that. For instance, for each, let me say, each case need a different discretization procedure.
Well,
to have the property maintained at the end, right?
Yes, yes, but fortunately for Lie groups in general, the discretization always follow the same rule. So it can work for Lie groups, but if you don't have a Lie group, then things start to become more and more difficult. But yes, those were the two main theoretical aspects that puzzled me when I was reading your PhD thesis. And from a more practical point of view, so you mentioned in your conclusions that you intend to implement some techniques for parallelization, such that you can implement everything on GPU or I don't know, maybe FPGA or other techniques like that. But have you thought about additional techniques? I mean, mathematical techniques in which you can reduce the complexity still further while maintaining the good properties that you achieved with constrained zonotopes. Because one of the tricks that you used, and which is quite clever, that you and your advisors and collaborators have been using, is that you can change from different representations when it's convenient. I mean, you have the GP. I don't know the acronym you use. You have the HREP and you have the VREP, something like that. So whenever it's convenient, you change some representation, do the calculations where it's more appropriate, and then you continue in the place where the calculations have the properties you want. Is that correct?
Yes, I mean, this what you're saying is what is done in the literature of convex polytopes. When you not using constrained zonotopes. The idea of using constrained zonotopes is to try to do all the operations efficiently without requiring this change in the set representation, because the change, the conversion itself is very expensive. In the literature of convex polytopes, some operations are very, very cheap in the matrix representation, and another operations they are cheap and efficient in the half space representation, but with other operations, if you need to do a sequence of different operations, you need to convert from one to the other. The conversion is very expensive. The idea here, we try to use a representation, which is the constraint generator representation, to do not rely on doing this transformation, unless we can think about transformations if the transformations themselves are efficient, which is not the case of convex polytopes.
Yeah, I get it. Actually, I kind of I didn't make myself clear the way I wanted to convey the idea. So there are some points in which you have to. I think when you have half planes and you have to solve some linear programs. So Professor Kawakami or Professor Scott mentioned that. So there are some places that you still rely on linear programs to solve some things, and maybe you can get rid of them if you find a way of getting rid of them, right? It's a kind of tautology in my affirmation. But yes, what I wanted to ask is, do you think there is another possibility to changing the representation? Not the representation you're using is very efficient. I get it, and you have nice properties when you need to do those three important operations: Minkowski sum, etc., etc. So, but for those parts in which you still rely on solving linear programs, do you think that you can do some transformations in order to change the representation slightly, and then do the operations you need without relying on solving those kind of linear programs, and then coming back, which would be cheaper than just solving the linear programs?
I think if we manage to find some kind of, a different representation, which is not, just to be clear, cannot be any one of the others, like vertex of half space, because the conversion to these representations from this directly is already very expensive. You need to think like new representation, brand new representation for that, and we will need to take care if the conversion itself is not expensive. Both ways. And if you manage to find that, is I don't know, maybe a jackpot. I don't know. It will be very nice. It will be very nice.
Okay, right. Yeah. So you provided the answer. So it's very difficult. It's very tough. I get it. Okay. Yes. So these are my main 3 questions. I have just a few comments about the text that I want to do here, but the vast majority of my comments are directly in the PDF. So afterwards, I'm going to provide you with this PDF, and then you can see it there. But one thing that I must confess kind of bothered me in terms of notation, it's the curly brackets that you use for zonotopes when you use the abbreviated notation, when you have so in the beginning. So yes, so when yes, exactly there. So when you use curly brackets, usually we use curly brackets to represent sets, and sets do not consider multiplicity nor ordering, which means that when I see z equals curly brackets g sub z c sub z, what I see, I understand the motivation of using curly brackets because a zonotop is a set. Okay, I get it. But because afterwards you start doing operations on zonotops, I think it's quite awkward to represent them using curly brackets because all I can see is a set. Therefore, G sub Z, C sub Z equals C sub Z, G sub Z for me, right? Contextually speaking, if I take into account the context, of course, I know this is a zonotope. I do not see those 2 elements here as elements belonging to a set, right? Mm-hmm. I try to follow your nomenclature. Okay, that's fine. But still, I would use something different. I would use parentheses, because when you have, the representation using tuples respect both the ordering and also multiplicity, right? So, for example, you know what I mean?
Yeah, I just need to remember exactly what means the word. It's the word multiplicity. But I understand what you say, because this is like I'm saying could mean, because in the standard notation, this means a set with 2 elements, right? G and C.
Yes, but if you have G, C, and C, it's still the same set. Because the set, if you open curly brackets and put 1, and then you open the curly brackets and put 1 and 1 again, it's still the same set, because you cannot repeat elements within a set. Otherwise, you would have a multi-set. So in a set, you don't consider the multiplicity and you don't consider the ordering. Therefore, I find this notation inadequate, honestly. I would use parentheses, and if you want to convey that this is a zonotope, I don't know, use parentheses, and as a subscript, use, for example, Z to indicate that it's a zonotope. In the same way that we use subscripts to differentiate between different norms. For example, if you have the infinity norm, the 2 norm, the 1 norm, usually you have, the parallel lines, right, to represent the norm, and as a subscript, you use just, something different. This is minor. Of course, this is minor. From the context, I couldn't see anything strictly wrong from the semantic point of view, because I knew the meaning. But from the syntactic point of view, my brain is just trying to look at it and see a set. That's the main problem, right? But this of course is a minor point. But just to clarify those points. And the other thing I would like to say about the text in general, it is very well written. So congratulations for you. It's very well written. But there are some parts that, I don't know, I think you could improve a little bit more. So for example, if you go to section 6.1, please. In the problem formulation. Yes, so in this section, I was expecting a problem formulation. But here you have just your system description, right? If you read the text, you say, consider a discrete time system with nonlinear dynamics and linear measurement given by those two equations, and then you explain those two equations. But that's it. If you go...
You're correct, yes.
Yes, and then you continue with the passive fault detection, and there is no problem formulation there, right? The problem formulation, at least for the passive fault detection, appears in section 6.2, because then you describe 6.2, 6.3, and then you say, well, now to see if there is a fault, I verify if 6.4 holds, right? Mostly. And that information should be in the problem formulation. What is the fault detection problem, right? Do you agree?
Yeah, I agree. Yeah, I agree.
Okay. Yes, but honestly, this is just a few places here and there that have this kind of problems. But in general, it's very well written. One can follow it. I would say, I wanted to say quite easily, but then I stopped in the middle because sometimes it's not so easy to follow, but I understand that, the thesis in general condenses a lot of information. I'm aware of that. But for the complexity of the thesis and all the subjects that you considered, I think that it's quite readable. So congratulations. It's not a trivial subject. That's what I want to say. From the complexity of the subject, it's very well written and quite readable. So congratulations on that. And from the written part, I think it's. I think I covered everything I wanted to cover. The other things are completely minor, so they are in the PDF, as I mentioned before. But I would like to make some comments about the presentation too. So first, Brenner, it was too fast. Too fast. The presentation was, the speed of light. And it was somehow difficult to follow. And I understand that you try to cover everything you developed during your PhD studies, but in that case, I honestly recommend, because now you're going to make a lot of presentations and do presentations everywhere about your work. Try to instead of covering everything, pick the parts that are more important and cover just them, because otherwise it will be quite difficult to understand everything, right? I don't know, it's impossible to teach from scratch. This is a PhD defense. It's not a lecture. I get it, but try to focus more on the most important parts, because otherwise you have to speak very fast and it's difficult to understand everything you say. And my last question, because I was completely curious, so what exactly did you want to convey when you presented the video of the UAV carrying the load? Because you showed different steps in the motion. So you showed now it's a straight line and then there is a disturbance. But what what exactly I was supposed to see from that video?
I agree that video would be more complete in the sense of information, since you have like the trajectory, the desired trajectory plotted in the video. Then there will be very clear that the video, the objective was to show that the loader was being able to track the trajectory, even when subject to disturbances, it will be following the trajectory. However, we don't have the desired trajectory shown in the video. In the simulator, we still need to develop this part to show the trajectory. Maybe maybe I don't know if maybe it should be better to have shown the figures of the tracking error, or maybe put the tracking error together with the video, something like that. But just to show that the load was following tracking the trajectory.
Okay. Yes, I imagine that was exactly what you wanted to convey, but I wasn't sure, because you precisely described what I think it would be the best approach. I think that one thing to do in those cases is to show the video, and even if the simulator does not allow you to put the trajectory and the zonotopes together with everything, maybe what you can do is to put two videos synchronized. Of course, you have to edit them. So what you do is to put the trajectory that the vehicle is following, and then you put a trajectory tracking below, showing that for that specific point in time, the state is given by, and then you show the information you want to show, like the position, and then you show the bounds, and this can be quite nice. But again, this was just a comment for you that, of course, does not affect my evaluation regarding your work, which is impressive. Again, it's a very good work. So I congratulate you and your advisors, Professor Guilherme Raffo and David Raimondo. It's a very impressive work. And again, yeah, congratulations. So I finish here. Thank you.
Okay, Bruno. Thank you very much for your considerations. All the very precise, and you went to the point many times. So thank you very much for the comments. You try to put everything in the final version also. Okay, so thanks so much. So now I pass to the last member, the last external member of this examination board. So I'd like to thank you, Professor Bruno Teixeira, for accepting this invitation. And so it's a pleasure to have you here with us. So Brenner is with you now. Thank you.
First, I'd like to thank Professors Raffo and Raimondo for the invitation. It was a very good experience reading the final work of Brenner. As all the other members of the committee have said before, I was really impressed with the amount of work he has produced. Of course, many contributions to the field. It's very interesting to check all the references that he cites, because most of them are really in the last years, meaning that there are a lot of people, not a lot, there are a lot of publications on this topic being investigated very recently, which in one sense makes the work very motivational, but on the other hand as well, knowing that there are a lot of people working on the topic, it's a big challenge to work on the new ideas and to make them as final papers. Well, as all the other members have said as well, I really enjoyed the reading. I think that the document, the thesis, is very well written. I enjoyed as well the way the presentation was structured. It allowed us to have like a general view of the work. And now, I mean, as a member of the committee, I've selected 4 questions to make to you. Some of them are very simple. Some of them are just to really make you more intrigued about things that you could work in future, or things that made me feel very curious about, next steps. And so let's now address these 4 questions. Well, the first of them regards a point that you investigate in some of the chapters about the choice of the approximation point. You worked on many different ideas depending on the method. And when you work on constrained zonotopes, there is this thing that the center may not be inside the set, which makes the center probably not the best choice to work as an approximation point in the implementation of the method for nonlinear systems. But there is another question that is related to this one, which is, even though the problem here is to look for tight enclosures to represent the state estimates, when we think about applications, we are interested in a punctual state estimate. So selecting a punctual state estimate from a symmetrical set as a zonotope may be quite simple. We could choose the center, but this is not the case when you work with constrained zonotopes. I think this point here is somehow related to what Professor Kawakami has said about the transportation load example, in which you used a Kalman filter-based idea to select a state estimate for your problem. And maybe you could use as well some of the ideas that you employed as a choice for the approximation point to yield a punctual estimate as well. And when I think about that, I always have in mind a trace of parallel with the stochastic problem, in which sometimes we use the mean as the state estimate, and it's a pretty good state estimate, especially when you have symmetrical PDFs. But when this is not the case, especially when you have multimodal PDFs, the selection of the mode must be the most often used punctual state estimate. So since you have tested many different choices for the approximation point, now how would you suggest like a further work on choosing a punctual state estimate from a constrained zonotope state estimator?
All the proposed choices for the approximation point, they were based on the idea was to find a point inside the set that the resulting enclosure were less conservative, based on the way that the enclosures are computed. Now, in the case we choose the point for state feedback, that was the application in the case of the WV. Thinking, I don't know, maybe thinking in what was the original idea was to have like a input, like a sequence of states that have some kind of smoothness, not exactly searching for the minimum variance point, what has done more or less with that approach. Yeah, maybe something can be derived from the proposed approximation points, but not exactly with the same criteria. The same criterion, because the criterion is to reduce the size. Probably rely on some, as the approximation points, I'll rely on the solving linear problem. You know, maybe if you can consider to relate the point chosen time k to something that relates to the point that was chosen to time k minus 1 to have some kind of smoothness between the 2 points. Maybe can be formulated in terms of a linear problem. I don't know, something related to us without tackling going to the hybrid approach, which is not the original objective. You know, something like this. We haven't going to this direction yet,
Yeah.
but maybe could be formulated. But we need to think of the sequence of states that we're choosing until that point. Otherwise, I don't know if there is a clear criterion to choose the point inside the set.
All right, thank you, Brenner. And actually, I didn't expect you to cover this point on your work because you have already investigated so many interesting problems inside your thesis, but I was just curious about that. But now I have a question about what you have done. I would like you to open on page 60. And you have assumption 5.1, which was already somehow explored by Professor Dono. And you say here that you assume that your initial condition satisfied the invariant, which is quite reasonable assumption. But it seems here that you also assume that your process model is compatible with your invariant. What I mean here is that when you use physics to derive your process model, probably you will have a model that really satisfies this environment. For example, if you employ conservation laws, it's this information is somehow included in the process model itself. But in some practical problems, you do not work with this kind of models, but you rather use identified models. And probably when we work with set-based state estimators, that might be the case of using simplified models to somehow make the application more possible to be really implemented in some embedded system. And at the same time, this model was simplified and it captures the dominant dynamics of the system. It doesn't satisfy the invariant itself. So in this case, enforcing this information may be even more important. I would like you to discuss about what are the implications of not attending the assumption 5.1, of having a model that is not compatible with the invariant. Will your method work? Will the consistency step be enough to enforce this information that was not available in the model?
Okay. In the case that the dynamics do not satisfy the invariance, I think that when this is not satisfied, at least not exactly, maybe it's can be addressed by moving to the method proposed for the joint state parameter, not because of parameter part, because here the nominal will not assume the assumption is not make the same assumption. We'll have a disturbance variable that appears also in this constraint. So I think this allows some kind of slacking for the constraint to accommodate this kind of discrepancy on the model invariant. The methods in chapter 5 will not be able to be applied because since it is not satisfied, I expect that at some point the set will be empty when you try to refine the invariant.
Right. Again, this was just another question to make you think about, extensions of your work. That's what generally is done. You relax some of the assumptions and try to improve the methods to cover a larger, amount of systems. And now another question. It's about the mixed isotopes that you present in one of the last chapters. I didn't understand why you explored this idea, only for descriptor systems, because for me it seemed like it was a very powerful tool to represent in a unified notation different types of sets And since some of the set-based state estimators, they combine these representations, intervals, the boxes and the zonotopes, the constraint zonotopes, if you write all these sets in a unified parameterization, it may make the work somehow like easier, or at least more easy to follow, or at least more elegant. So why this more general class was not used in all the other parts of your work? Like, for example, one of the first presentations, and you structured all the methods according to this idea.
The main reason is because this was the last, chronologically, this was the last idea that we.
That's what I thought.
That you get in the thesis. But for instance, this could be applied to linear systems, not only the descriptor. I mean, the idea appeared in the context of descriptor systems, but could be used for linear systems. And we have proposed a future to use this for nonlinear systems as well. But that is a big challenge. What is the big challenge? When we let me see, I access just one of the methods here. Sorry, the new value extension. For instance, I'm going to be able to show this. Okay. The problem is, no, I will not be able to show the equations here, but to compute the remainder of each one of the approximations, we evaluate the remainder term, for instance, for the interval rule of the set, right? To have a guaranteed enclosure, right? The problem is that if you use a mixed zonal tope, it can be unbounded. If the set is unbounded, I mean, just showing what is the main challenge to implement this with mixed zonal topes. There is in the future work, I don't know how much work is needed to solve this challenge, is to bound the remainder for an unbounded set. Or just, maybe you can expect an unbounded remainder. But how conservative is this? We cannot compute the interval rule of this set anymore because the set is unbounded. There is no interval rule, at least in one direction. So yes, this is the last idea. You need to, run the doctoral course, my doctoral course again over this new set representation and see how to solve something like this.
All right, thank you. I imagine that was the answer. And then in the last months, it seemed like many different ideas just pop out of the papers that we write, and sometimes there is no time enough to come back in the first contributions and present them from a different perspective to make them more general. But it seems to be a very interesting topic as well for you to investigate in the future. Now I will come back to a point that Professor Kawakami asked when you was investigating the problem of joint state and parameter estimation. You mentioned about unknown and constant parameters and the algebraic variables. And well, first I thought that when you have like the variable key, since it is constant, that somehow it was treated like a scalar and no uncertainty for it was actually represented, which is not the case, because in the examples that you investigate further, you define bounds for both p and lambda. So I mean, I understand that this is what you call the algebraic variables. The only difference that they are not assumed to be constant, that they vary a long time, so they could account for maybe unknown inputs of the system that you would like to estimate. They could be time varying parameters as well. They could be unknown disturbances that you needed to estimate. But my question is, inside the method, I mean, how the variables p and lambda k are treated? They are treated in a different way so that p is estimated like really as a constant, and the other one you could follow the time variations.
Now, the difference is that for p, for p we have a dynamic law, which is that is p being constant. In the case of lambda, we don't have any dynamic law that we use, for instance, as a kind of prediction for the variable. We rely what we do with the algebraic variables is we assume a known bound for each time instant, and what we can do is to refine these bounds using only the algebraic constraints and the update step. We do not have the dynamic law available for these variables.
All right, I understand. So in the first case, P, you just say that Pk equals Pk minus 1. And you enforce this information during the estimation process. I mean, you treat it almost like an extended state variable that during prediction, you say that its value keeps constant and you estimate it, all right?
Yeah.
All right, exactly. I got it. Just a final comment, I mean, you use from the abstract until the conclusion the term unknown but bounded. I was kind of annoyed by this expression because when you have an uncertain variable, by definition, it's unknown. It's uncertain. You may somehow parameterize its uncertainty. For example, using a PDF in the stochastic scenario or using a set in the set-based scenario. But why this term unknown but bounded is used? Would only bounded be enough, or is that redundant? Does other papers use this terminology and you just use it as well? Is there any reason for that?
We use this term just following because the terminology this terminology is common in the literature of set-based state estimation. However, yes, the uncertainties, I agree, the uncertainties are unknown by the definition, otherwise we would not be uncertain, certain variables. So I think maybe the idea of using this term unknown but bounded is to mean that the only thing that we know about the variables is the bounds. But is a redundancy the unknown if we be certain variables? I agree with that. But we just following, I mean, this is common in the literature. We just follow the nomenclature. But I agree with the questioning that we're making because it's like a redundant nomenclature if you are already talking about uncertain variables.
All right, that's all. I just would like to thank again and congratulate Brenner for the awesome work you have developed during the last years. And I think that from now on, you could just look back at your work and be very proud of it. It's very clear from the presentation and from the document here that you really worked seriously during the last 4 years, and you took the best of what you could have done, and you have achieved a lot of interesting results. And so I am sure that you will have a lot of work to do afterwards. And I mean, that's the main purpose of the PhD itself. I mean, it's preparing you to new research independently from now on. So congratulations, and I return the work for Professor Huff.
Very much. Went to the so thank you very much for that. Now we have the last two members, the advisors. So I'd like to know if someone has any more comments. Professor Joseph, you commented before that maybe you would have some comments at the final. I want to say something and comments.
No, I mean, I was originally afraid that some of the other comments would make me think of more things I wanted to say, but I think everyone did a comprehensive job. The only comment I have to add at this point is following up about the curly braces notation for the zonotopes and constrained zonotopes that's used. You can blame me for that. That comes originally from the first paper on constrained zonotopes. So that was my mistake, and I was cognizant at the time that might be interpreted, as the set containing two elements, G and C. But I have to say I have the same problem with the tuple notation, because if you use parentheses, right, then it looks like a tuple, with one element in Rn by n and another element in Rn. And that's also not the right thing. That's not a set, right? So if I write that tuple is a subset of Rn, that's also nonsense. If you view it in the normal way, a tuple would be viewed. So I'm definitely open to suggestions of how we could be denoting that more clearly, but I'm not sure either of those options really is satisfying. I mean, maybe angle braces might be possible, but then, if somebody's going to think it's an inner product, and so it never ends. But thanks for the comment.
Okay, that's a good. Okay, I don't know if Professor Bruno's Teixeira and Bruno do Brenner or this nice discussion. Very.
Not really. I covered everything I wanted to. Thank you.
Yeah.
So did I.
Okay. Thank you so much. So now I would like to pass the word to the Professor Davide, who conducted myself, but Brenner during these 4 years and a half. I think I'm sure that Davide and also the collaboration with Joseph, his work not be so good as was, and so I'm sure also that Brenner is going as well. But so thank you, David, for that very nice collaboration. Our first collaboration. So please, Brenner is with you.
Yeah. So first of all, Guilherme, thanks a lot to you for inviting me to supervise together with you Brenner. So this has been a very nice journey, and I've been very lucky working together with you guys. And I have to say that I was very impressed by Brenner's abilities and skills. So I think it was very fruitful, the research we did together. And of course, this was possible only also thanks to you, Guilherme, and Joe, of course. So just to say, I'm very, very happy about the results we got together. And I think that I'm very happy, besides that, about the discussion we had today. And there are several things that we need to fix and improve. That's very good. And the discussion was quite intense and useful. I don't want to take more time because it's already quite long, the time we spent. I just wanted, Brenner, you to comment on so the weaknesses of the methods we have developed so far. So indeed, when we look at the first order method, or in any case, the linearization methods we have been using so far, we know that they do not work well when we have high nonlinearities, right? So I would like you to comment on this and to suggest, if possible, any alternatives that could be, let's say, less conservative from that point of view and applicable for real systems like the electrochemical model we have in mind for the batteries.
Okay, all these methods, they rely on kind of approximation of the remainder term, right? We either using within the mean value theorem or the Taylor's theorem, but with approximation to the first order. Yeah, maybe we could get more accurate methods if we search for, of course, different approximations. The problem is, if you go to a higher order, we cannot formulate, at least in principle. If you go to a higher order, if we are able to formulate in terms of constraint examples, we get more numbers, increasing number of generators and constraints, be more computational burden of the method itself, because we need to, since we have more constraints and generators, in order to reduce the complexity of the set, it will take much more time to do it. But maybe we need to seek methods that are not based on a Taylor approximation. For instance, there is a method based on zonotopes that uses the DC programming. This would be an idea, next idea different than those two approximations to try using constraints on zonotopes and see if you get better results. Also, we try to search for approximations that are not so general, that exploit some kind of structural properties in the names of the system. We are not doing that. We are just proposing very general methods.
Or maybe we have to go beyond the constraints on top, right? Looking for something that is not just described through polyhedra, right? That I think is the direction we need to further explore.
Yeah. I mean, I was thinking only in constraints on top, and but yeah, searching for a different representation that, for instance, not convex, because the reachable sets of the nonlinear systems in general are not convex. We're doing a convex approximation at the end. Yes, you get probably more accurate results.
Okay, so Guilherme, it's on you now.
Okay. So thank you. What I have to say is, Brenner is working for me. It's almost 7 years, years and a half from master thesis, and now for 4 years and a half in the PhD. So it was a pleasure to me to work with Brenner and also with Davide, and it's very, very nice. So everything we asked to Brenner did it in a very excellent way. Excellent. So I don't have anything to say more about the work, and I don't have a question about the question before. And so I just want to say congratulations to Brenner, because you should be very happy and all the results you obtain. Okay. From my side, is it? So now, if you be in present, I will pass the word to the audience, but we don't have any audience. I will have a lot in YouTube, but now the board don't have. So Brenner, we pass for the next phase. It's the deliberative phase. So you ask you to go out to this room, and I sent you a message for WhatsApp, for example, asking you to enter again. And also, Luciano, if you can, se pode colocar em deliberação. Ok, obrigado. Okay, Brenner. So the examination board made a vote, and by animals we decided to approve. And now you are a doctor, so thanks for the very great work, and congratulations for this very rich work that you did during this PhD. So I don't know if you want to say something. Oh, congratulations. Okay, now your turn.
I would like to thank first my advisors for the, it's 4.5 years work, this doctoral course and writing of the thesis. I would like to thank the advisors for the support in the discussions, the meetings, everything, the ideas, they helped me a lot. I also thank my the committee again for the accepting the invitation. I'd like to take the comments from the committee, the discussion that we had just had. I think it's very good. I would like to thank my colleagues. Despite of the let's say, with the pandemic, we don't have contact, but we're always in contact. I'd like to thank also some friends that I have in Pavia. For the time that I was in there for the doctoral sandwich, period. I'd like to thank David for the revised me during that period that I was in Italy. I'd like to thank all the collaborators. I'd like to thank Joseph Scott for the discussions, for the collaboration on some of the papers. And there's also a part was done in collaboration with people from Cyprus. I'd like to thank you for the collaboration with them as well. Diego for the collaboration in the part of the batteries. I'd like to thank also, I always far from my family because I'm in a different state. But also thank my family for the support during this period, this 4.5 years. And that's it.
Okay. So, and now we need to celebrate, to relax some days, just enjoy the time. And now you are a doctor and excellence. So, congratulations again.
Thank you.
Brenner. So, from my side, I don't know if someone wants to say something.
Guilherme, I just suggest you to ask Brenner about the title.
Yeah, Brenner. We removed the contributions from the title, and so the title will be just a set-based state summation fault diagnosis using constraints, sonotopes, and application.
Okay, it's all right.
Shorter and as just said,
It's supposed to be contributions already. It's supposed to have contribution in the thesis already, otherwise it's not a thesis. So yeah. Okay.
So and now from now on you have about 30 days to perform all the considerations and to present a final version. Secretary. So about that you can talk.
Okay.
It's just unfortunate we cannot see each other for real, right? So, yeah, and to enjoy the food in miniaturized, that is very good, as I
Yeah.
remember.
Okay.
Hopefully there will be another occasion soon.
Okay.
Okay, so that's it. Thanks.